Hello, we're going to talk a little bit about a definite integral. So previously we've been talking about Riemann sum, and that term, Riemann sum, that phrase, is just saying we're going to calculate the area under the curve by drawing rectangles, because we can easily calculate the area of an individual rectangle and we can add them all up. And we also said that the area of those rectangles did not need to be equal width subintervals, but they can be equal width. And if they are equal width, we can write a method for the sum that has a regular formula. So if we predefine some horizontal distance, some delta x, and then we evaluate the function at regular intervals along that delta x. If we add up all of those length and widths, which give us areas, that's going to give us the area of the entire region. And then we said, well, when we look at making n rectangles, we're looking at n approaching infinity, right? So those rectangles are all infinitely small in width, right? And so what that Riemann sum represents, the thing that we're going to start talking about here, is that it represents the definite integral. Okay, so the integral of a function. And what makes this definite is the fact that it has a lower and a upper bound, this a and b value. So I've pulled in this image here of a definite integral. So we still have our integral sign, right? That still is going to be in front. And we have our integrand and our variable of integration. And the only thing that we're adding here is the fact that we have an upper limit of integration, b, and a lower limit of integration, a. Okay, so when we look at this, we would consider this to be the integral of the function f from a to b, or on some interval from a to b. So we've dealt a little bit with indefinite integrals, indefinite. And when it's indefinite, there are no bounds, a and b. But a definite integral has this upper and lower limit. So here we have some rules satisfied by definite integrals. And before we can actually do calculations and find definite integrals, we need to make sure we understand how we can manipulate them. So the first one we have here is very important, and it represents our order of integration. And so essentially what the order of integration one says is that if my bounds are reversed, notice I have a as my upper bound and b as my lower bound. Okay, so normally we would have a and b, but in this case they are reversed. So what this says is if my bounds, if I don't like the way they look, and I prefer to write them, switch my bounds, write them in the other direction, I can just negate my integral. And this is a really important definition, and we'll use it a lot in our calculations in order to simplify what we're looking at, or to make it look like it's more of a standard form. Okay, so basically you can switch the bounds and you can negate the integral. So number 2 here says that if you have a zero width interval, so notice there's no distance between my upper and lower limit of integration. If there's no distance, then the area in that space of no distance is equal to 0. And so I've pulled in a picture that illustrates that. If you're going from A to A, there's no space between A. So the area under that curve in that space that doesn't exist would be 0. So our third rule is the constant multiple rule. And what the constant multiple rule says that if you have a constant in front of your function, you can pull that constant in front of the integral. So notice that k moved to the other side of my integral symbol. And I've illustrated that by pulling this picture in right here. And essentially, say if you had a constant 2 and you were finding your integral, your area under your curve for f of x, if you had 2 f of x, it would just be 2 times as tall. Our fourth property, the sum and difference property, simply says that if you have the integral of a sum of functions, then that is equal to the integral of each function, and then you add them together. So the integral of a sum is the sum of each of the integrals. And I've pulled another picture in for us. So what we can see is we have our integral f here, which is the blue integral, the area under that curve f of x. And then I have g of x, which is all of this area. And if I were to add those two integrals together, I would get the green region, which is just, since f of x was constant, f of x taller all the way across. Our fifth property here is the additivity of integrals. And so we want to make sure we pay very close attention to these bounds. So if we choose some b value between a and c, we can rewrite that integral as a sum of two integrals. And this one's really well illustrated with a picture. So if we look at what I've grabbed here, the integral from a to b of f plus the integral from b to c of f is equal to the integral from a to c. And so when we start talking about curves that may go above and also below the x-axis, they may cross over the x-axis, they may cross over each other, and we're trying to find these areas, there might be situations where we need to split integrals up. So starting with a big integral and breaking it up into two smaller ones by some predefined b value somewhere between a and c on that interval. We have our max-min inequality, and really all that says is that an integral is bounded by a maximum area and a minimum area. There's an area that can be created just above and also an area just below. So an integral can be between any two area values. And we can see that here, that blue area under our curve for f, it's bounded by the green below and the orange above. And our last rule here, domination, says that if the function f is always greater or above the function g, then the integral for f, the value of the integral, will always be greater than the value of the integral for g. And so in this last picture that I've brought in, example f here, you can see that the function f is clearly above g everywhere. And what that tells us is the value of the integral will always be greater for f than the value of the integral for g on that interval from a to b. So just to recap, we have several important rules here, but the most important ones, I think, for you to understand are going to be, number one, changing that order of integration and negating the integral, and then also this additivity rule, which says we can split an integral and write it as two smaller integrals, or vice versa, take two smaller integrals of the same function and add them together to give us a total integral value. So let's do an example that illustrates how we can use some of these properties. So suppose we have these two functions, f and h, which are both integrable, and that we know these three integral values. So in red, the integral from 1 to 9 of f of x dx, equals -1. The integral from 7 to 9 of f of x dx equals 5, and the integral from 7 to 9 of the function h of x integrated with respect to x equals 4. So we know these three values. Let's see how we can conceptually find some other integral values using a few of our properties from the previous slide. So my first example here might be, well, if I wrote 1, the integral from 1 to 9 of -2 times the function f of x dx. So what I know is that that 2 is a constant multiple, and this can be rewritten as -2, the integral from 1 to 9 of f of x dx. And of course, that is given to us in the problem up above. So this would just become -2 times -1. -2 times -1 gives us a value for this integral that would be +2. So let's do another example. In this situation, we have the integral from 7 to 9 of f of x plus h of x, both with respect to x. So that, by our properties listed on the previous slide, lets me know that I can write this as the integral from 7 to 9 of f of x dx plus the integral from 7 to 9 of h of x dx. And of course, those two integral values are given. The first one is 5 and the second is 4. So the sum of those two is 9. So the integral of a sum is the sum of the integrals. So expanding on those first two examples we just did, let me write this one. We've got the integral from 7 to 9 of 2 f of x minus 3 h of x. So I can separate that and write that as 2, and then we would have the integral from 7 to 9 of f of x dx minus 3, and that would be the integral from 7 to 9 of h of x dx. So because I had those two constant multiples, I pulled each of those in front of my integral symbols. Addition is the same as subtraction, so we can apply that sum rule that we just used. And then the other thing I like to point out is notice that all of this was in parentheses times the dx, that variable of integration distributes. And it's really important that you make sure you write that every time. And moving forwards towards Calculus 2, you can have different variables of integration. Most of what we will be looking at in this class, everything will be given in terms of x, and then the variable of integration will be in terms of x. But continuing through, I know those two given values, so this gives me 2 times 5 minus 3 times 4, and that is 10, take away 12, or -2. So our fourth example here, this is a really important one to make sure we understand. It's the integral from 9 to 1 of f of x dx. And this one's really important because it involves the order of integration. And you'll notice my lower limit is actually a larger value than my upper limit. 9 is bigger than 1, 9 is lower, 1 is upper. And so what we know is that we can rewrite this and we can negate the entire interval integral, we can negate the entire integral when we switch those bounds, make it from 1 to 9 of f of x dx. So this would be equal to negative 1. So negative 1, this integral value is positive 1. Here we have a fifth example, 1 to 7 of f of x dx. And so paying attention again to our limits of integration. This goes from 1 to 7. And if I look at what's given, none of my given limits, well, don't need to concern myself with h for this problem because we only have f, but none of my given limits are from 1 to 7. I have 1 to 9 and 7 to 9. And so here we can use our additivity property of integration. And in this situation, I could say, well, this is going to be the integral from 1 to 9 of f of x dx. So it's going to equal that minus the integral from 7 to 9, because I only care about 1 to 7, so I can take 7 to 9 out, and that's of f of x dx. So in this situation, I end up with negative 1 minus 5, which gives me negative 6. And so our sixth and final example in this video, we are going to do the integral from 9 to 7 of h of x minus f of x dx. So again, pay very close attention to your limits of integration. All right, those are in the reverse order of the way we expect them. So one thing that I can do is negate my entire integral and say this is negative the integral from 7 to 9 of h of x minus f of x dx. Now, as we split this apart, we want to make sure we note the negative is in front of everything. So this is equal to negative the integral from 7 to 9 of h of x dx minus the integral from 7 to 9 of f of x dx. So I can calculate each of those two values, and that would be negative. H of x is 4. Take away the f of x integral, which is 5. So that gives me negative 1, and negative 1 is just positive 1. So we have talked about what a definite integral is. We have also mentioned, some properties of integrals that we need to be able to use.